today we're going to take a look at section 10.5, which is area and arc length, specifically in polar coordinates. So a lot of what we're going to be doing right now here at the beginning is sort of developing the process by which this makes sense, given other pieces of information we've done before. So we would like to compute the area enclosed by a polar curve. Because such a graph is not a function of the form y equal f of x, we can't do things the way we normally would in chapter 5. And while we could convert our formulas from 10.2 into a simpler approach uses the following geometric argument. All right, so here's the argument. Recall that the area of a circle with radius r and central angle theta is area equals pi r squared. And the area of a sector of a circle with central angle theta would involve the ratio of the sector to the circle, theta over 2 pi. All right, so that's our angles ratio. So the area of a sector would be the pi r squared times the ratio theta over 2 pi. And if we simplify that, we get 1/2 r squared theta. Now you could just look up that the area of a sector is that too. I mean, that's fine, but that's where it's coming from. Area is 1/2 r squared theta. Okay, now consider the area enclosed by a polar curve that's defined by r equals f of theta. And the rays, theta equals alpha and theta equals beta, where f is continuous and positive on the interval from alpha to beta. Okay, so far so good. So we're looking at a specific sort of sector. The sector goes from alpha to beta on the curve f of theta. And what we do is the same thing we would do with rectangles back in the chapters 4 and 5. So we partition the area into sectors, and the width of each subinterval is delta theta equals theta sub I minus theta sub I minus 1, which is beta minus alpha over n, and n is the number of subintervals. Okay, so beta and alpha are the full sector's value, and n is partitioning that into a bunch of subintervals, much like we would go in chapter 4 and 5 from A to B, and we would make n subintervals there, right? So in each subinterval, we can approximate the curve with a circular arc. Now, this is kind of akin to making rectangles, right? We're making sectors that are circular, just like we were making rectangles, right, that had a specific height of them, and we let this go to infinity. So the area, a sub I, enclosed by the curve on this subinterval is approximately the same as the area of the circular sector of radius, f of theta sub I, with central angle delta theta. Okay, so I'm going to pause right there and kind of draw a picture of what we've been describing so far. So we have a sector that we're going to be using. Let's just make an arbitrary kind of image. It looks something like this, in polar form, of course, it's just arbitrary. And we have an angle alpha, so I'm going to use this one right here. So this is my angle alpha. And then we have an angle beta. So let's let our angle beta go up here. And so our beta is right here. All right, so here's beta. And we're talking about finding the area right in here. Let me shade it in for us. So this is the area. It's a thicker one. This is the area that we're looking to find, right? And of course, this doesn't look very circular on the edge, but can you imagine making a really tight curve instead? So let me take the shading out and put in a tighter angle. So imagine if we had it like this, right? This starts to look more like a circle. This angles being really tight and really small are like our rectangle's widths being very, very narrow. Okay, so back to what we're looking at. So the area a sub I, I'll read this again, enclosed by the curve on the subinterval is approximately the same as the area of a circular sector of a radius f of theta sub I with central angle delta theta. So the area a sub I, which we established earlier was 1/2 r squared delta theta, is now 1/2 f of theta squared, because that's the same as r, right? R is the same as f of theta times delta theta. The total area enclosed then is the summation of all of these little bitty sectors. So now we're looking at things that look like chapter 9. The sum A is summation from I equal 1 to n of a sub I, which is the summation from I equal 1 to n of 1/2 f of theta sub I squared delta theta. And as long as we've done this numerous times, we can improve the approximation by making n larger. Taking the limit as n goes to infinity, we have the limit as n goes to infinity of the summation from I equal 1 to n of 1/2 f of theta sub I squared delta theta, right? Same as we had on the previous screen. And this is equal to the definite integral from alpha to beta. That's a typo, so sorry. Get this out of there. So this shouldn't be there. Of 1/2 f of theta sub I squared d theta. Yeah, there we go. All that's correct now without that piece in there. Okay, so we've actually taken this and we've found a definite integral that we can find using the area of a sector formula as the integrand inside. All right, so the area in polar coordinates, putting all that together and writing that more concisely, now looks like this. So if f is continuous and non-negative on the interval from alpha to beta, then 0 is less than, 0 is less than or equal to beta minus alpha is less than or equal to 2 pi. And in other words, that the measure of the angle between alpha and beta is between 0 and 2 pi. Then the area of the region bounded by r equals f of theta, and theta from alpha to beta, is the area is 1/2 the integral of alpha to beta of f of theta squared d theta, or you could say r squared d theta. And boy howdy do we need an example, right? Okay, now these are a little tricky, and the reason they're tricky is because most of what we're going to be doing is going to look trig in nature, right? Because we're talking about things that are in polar coordinates, and that's when they're valuable. So we end up with some very interesting images. So if you take your calculator out, I'd like for you to graph r equals cosine of 3 theta. So make sure you're putting your back into polar mode if you've moved it out of there since we met last, and make your r to say cosine of 3 theta. And just so that we're on the same page, let's make our window go from 0 to 2 pi. That's usually kind of what we want to do, and see that. And we will let our t-step still be 0.1. And our window can probably go from a little bit smaller. I mean, this is only cosine of 3 theta, so my values can only go between -1 and 1. So probably letting x go from -2 to 2 and y go from -2 to 2 will work. And if you graph this, you get a very interesting shape, one that you've probably not worked with before. I'll sketch it on the screen as well. It looks something like this. So it looks like kind of like a flower, a 3-petaled flower. And so the way that it's being described here is we're going to find the area of one leaf of r equals cosine of 3 theta. One leaf. So in other words, in my picture right here, we're looking at finding one of these petals or one of these leaves, not all 3. So we have to make sure that we're getting angles that make sense. And now if you watched this as that graphed, you might have even noticed that it went on top of itself, right? It didn't even, 0 to 2 pi, actually, it overlapped even itself a little bit with the 3 petals. So we need to actually just get 1 petal. So our image, actually, we want it to look like this. That's what we're trying to find. So how do we do that? Well, one way is that you can sort of arbitrarily play with the angle measures for your theta. That's not a very time-effective way to do this, and there's a much easier algebra way to do it anyway. So what we want is we want the cosine of 3 theta to equal 0. Now why 0? Well, because 0 actually means that we're at the origin. So if r is equal to 0, we're at the origin. And the origin is where each of these petals or these leaves will start and stop. So we want the cosine of 3 theta to equal 0. Now cosine equals 0 when the angle itself is equal to 0. I'm sorry, not equal to 0. The angle itself is equal to pi over 2, 3 pi over 2, and so on. It will continue on beyond that, right? So we will actually let this go between those values. Let me move this up just a little bit. So this is because of the unit circle telling us that the cosine values are going between pi over 2, 3 pi over 2, and so forth. If this said sine of 3 theta, we would be using 0 and pi and 2 pi, right? So we're going to divide by 3. So my theta is equal then to pi over 6. We can go 3 pi over 12, excuse me. Did I write that? No, 3 pi over 6. I had that right the first time. So 3 pi over 6 is the same as pi over 2, right? So otherwise known as pi over 2 here. And there's going to be others, right, too. But 2 of them is all we need, and it should make that work. And we can actually test with our calculator to see that whichever version you want will work. So if you let your window now go, instead of from 0 to 2 pi, have it go from pi over 6 to 3 pi over 6 or pi over 2. And if you graph it, you'll get one leaf. Now, it's not the leaf that I was anticipating, but it doesn't really matter. The leaf I'm getting is actually down here in the bottom corner. Okay, I keep trying to draw it. Let's try one more time. There we go. This is the leaf that I'm getting from my image. But that's okay. I only need one leaf. That leaf will work just fine. So as I'm making my area statement, this is going to be equal to 1/2 the integral from pi over 6 to pi over 2 of the cosine squared of 3 theta d theta. Okay, now here's the deal. I mentioned this in section 10.4 as well. I'd encourage you, again, if you haven't already done so, to print off the trig substitutions, not substitutions, but trig identities, rather, that are inside of Canvas. This is a squared cosine. We don't have a direct trig antiderivative for squaring cosine. We actually need to change this, and we need to change it into something that's workable, and we can do that with actually double angle identities. So let me shift this down so I have a little bit more space to work, or a little bit more, yeah. So I give myself more space to distinguish these work anyway. So if you take a look at the trig table, I'm going to move the 1/2, I'm going to move keep the 1/2 in front, and I still have pi over 6 to pi over 2. That's not changing. But if you look in the table, the double angle formula actually says that if we use the cosine, of 3 theta squared, this is equal to 1/2 double the angle, which is 1 plus cosine of 6 theta. That's the substitution. It might actually say, like in the table, it won't say 3 theta, right? It'll say the cosine squared of theta, and it'll say that it's equal to 1 plus cosine 2 theta over 2. So this is our version of it for our angle 3 theta. So we have this, and now we're going to take an antiderivative of that. Now that we have cosine just by itself, we have a very simple u substitution. Feel free to do the u substitution if you'd like, but if you can see it without doing it, that's fine too. So I've got 2 1/2s, the one that's in front and then the one that's in front of my parentheses. And then I have the antiderivative of 1, which would be theta. And then I have the antiderivative of cosine of 6 theta, which would be 1/6 sine of 6 theta. Okay? And we're going to evaluate that at pi over 2 and pi over 6. We're going to plug pi over 2 in, we're going to plug pi over 6 in, just like we would with all of our others. So I have 1/4 at the beginning. I have pi over 2 plus 1/6 sine of 3 pi, and then minus pi over 6 plus 1/6 sine of pi. So this is what I have, multiplied by my 1/4. So if we simplify this a little bit, work out a little bit of that arithmetic at this point, really. I mean, it's complicated arithmetic because there's pi's in it, but it's arithmetic. We actually get pi over 2 minus pi over 6. Pi over 2 minus pi over 6 is pi over 3. So this is 1/4 times pi over 3. Or the grand total of the area is actually pi over 12. So one leaf, or one petal, depending on what resource you're looking at of this, has an area of pi 12ths. Okay, so we're going to look at another one. These feel a little bit different depending on the image that you're looking at to start with. This one is not just a cosine of 3 theta, right? It's not just a single piece. It's actually got addition with it. So go ahead again and take a moment to graph this. So you're going to put into your calculator 1 plus 2 sine of 2 theta. And because we don't know right now, we're going to go from 0 to 2 pi and see what we get, because 2 pi is going to give us the entire image, but maybe more than we need because this is actually a double angle, right? It says sine of 2 theta, but we can at least see the image. Oh, when I did that, it didn't look very good because my window's not big enough. So I'm going to extend my window out, my x min, x max, and so forth. I'm just going to go from -5 to 5. I think that'll probably be plenty on this one again, and give that a try. Okay. So you're getting something that looks kind of like, you know what it looks like is like those propellers that come off of the trees. Those are little propeller leaves that fall down. That's kind of what mine looks like anyway to me. So it looks something like this. Oh, not like that at all. Let's get a straight line there. That's better. So we have some big leaves, right? They look like this and like this. And on the side, we have these little tiny ones here and here. So it looks something like that. Kind of almost looks like the way I've drawn it, like even like a bow tie or something like that. Okay, so we can inspect the graph a little bit. We want to make sure that we're getting, again, these angles that come back to 0. So we have 1 plus 2 sine of 2 theta, and we want it to equal 0, right, because the r is equal to 0. If we simplify this a little, we have sine of 2 theta is equal to -1/2. And -1/2 values for sine, right, of the angle make it happen at the angle, which is our angle is 2 theta. And I'm going to write down a few of them. We can put 7 pi over 6. We can, keep going from there. We can actually go backwards on this one. That's actually kind of helpful, so I'm going to do that. We can actually go to negative pi over 6. So from 7 pi over 6, we could go to 11 pi over 6. We can go to, I think I missed one along the way. Let me see. Oh, I didn't because it's negatives. I was thinking about the other ones that are in the positives. This would continue, like we could go backwards, not just to negative pi over 6, but we could go backwards further than that. But there's others in both directions, of course. So we need to inspect the graph. If you thought you were just doing the positive ones, which would make sense that you might try that, you just see 7 pi over 6 and then 11 pi over 6. If you put in 7 pi over 6 into the theta min and put in 11 pi over 6 into theta max, and you graph it, you get this sort of strange image that doesn't quite do what you expected it to do. One caveat to this that I didn't think to mention, I thought I was one step further than I was. So sorry, before we look at the graph, we need to still divide by 2. So sorry. Let's get that done. So we have negative pi over 12, 7 pi over 12, 11 pi over 12. Now let's look at the graph. That will make much more sense. All right, trying again, window. So sorry. Let's try the 7 pi over 12, which is what I was trying to do, and then 11 pi over 12. Okay, so if you look at that, you actually end up getting the little loop right here. That's the loop that you get from 7 pi over 12 to 11 pi over 12. So let's change that. Let's let our window go from the negative pi over 12 to 7 pi over 12 and see if that will actually give us the loop that we want. And if I graph it, in fact I do, I get this loop now. If I had gone the other direction, that would have been fine too. Right, I didn't write these out, but there's going to be another one over here. So after 11 pi over 6, we would add to this, so we'd have 19 pi over 6, I think. And we could have gone from 11 pi over 12, and then it would have been 19 pi over 12. So we're choosing to use these two, but if you had chosen to use these two, we'll check it real quick. I think that would work as well. Indeed, if I do that, I get the lower circle or leaf down here. So either one will work. The one that we're going to use is just going to be that first one. So we're going to use this one right here. All right. It doesn't really matter. You'll get the same area when you do this either way. But moving on then, I have my area, and I'm going to let my area be the 1/2 then, and it goes from negative pi over 12 to pi over 12. Okay. So this is kind of some messy trig substitution steps. That's why you've got more space on this one on your paper, and I'll probably have to shrink something and move something around to make space on mine as well. In fact, undoubtedly I will. So let's just do that right now and shift this up, and then I'll have more space to work. And I will shift my picture up as well. Put it up here in the top corner. Okay. I guess I moved my bit of my equation when I did that by accident. We'll get that over here. Okay, all that work to fix an A. Oh my goodness. All right. So we're taking the 1 plus the 2 sine of 2 theta, which is our formula. We're squaring it and we're doing d theta, right? That's our goal. So squaring this involves, of course, FOILing out. And so we have our 1/2 integral from negative pi 12ths to pi over 7 pi over 12 is what it's supposed to be, right? Yep, I messed that up too. There's my 7 pi over 12. So sorry, there we go. 7 pi over 12. So if I multiply this out, I get 1 plus 4 sine of 2 theta, and then I get plus 4 sine squared of theta, of 2 theta, sorry. Missed that 2 in there. Okay, so that's all well and good, but it's much the same as when I had this one last time, right? I've got this cosine squared here, and now I have a sine squared here. And so I can go back and I can look at, they're called power reducing formulas. You can also see them in the double angle formulas. Sometimes there's different versions of them that allow you to go one direction or the other. Power reducing is what you're going to see this one underneath on that chart. And so we have the 1/2 integral from negative pi 12ths to 7 pi 12ths. And then with the power reducing here, I have 1 plus the 4 sine 2 theta, like that's nothing different. But then in power reducing this, I have a 2, and I have 1 minus the cosine of 4 theta. Okay, that's the power reducing formula that I will need. And I'm going to clean up just a little bit. Oh, I forgot my d theta up here too. I'm going to clean up what's inside here just a little bit before I take my my antiderivative. But it doesn't need a whole lot of cleanup, right? So like this 1 and then this 2 right here will simplify. That's kind of what I'm talking about. So much of this is the same as what we already had. So we can just put that back down again. The 1 at the beginning and the 2 in the middle give me a 3. And then I have plus 4 sine of 2 theta. And now I have minus 2 cosine of 4 theta. And I didn't really mention this very well before, but the reason that this 2 came about is because there's a 4 here, and the power reducing formula has a division by 2, so it changed this into a 2. So that's where that 2 came from. And then we're going to integrate. Okay, so we're going to be able to integrate this now. So the part at the beginning, we'll just have a 1/2. And then the antiderivative of 3, of course, is 3 theta. We have some simple u substitution. Again, write it out if you need to. But the 4 sine 2 theta will become negative 4, and then cosine of 2 theta over 2. And then this other one will become it'll stay a negative 2, and then the cosine will become a sine of 4 theta over 4. And we're going to evaluate that at 7 pi 12ths and negative pi 12ths. And as predicted, again, I even ran out of more space. So I think I need to continue this last step onto another slide. I don't have another slide built in, so I'm going to get one at the very end and just use that. I'll fix that later when I rewrite my notes. All right, so here's where we are. We'll just continue from here. You've got the space on your screen, so or on your paper if you've written in a reasonable font, or not font, but a reasonable typeset size. Okay, so I have 1/2 in front, and then I'm putting in the 7 pi over 12. So I'm putting in 7 pi over 12 to the 3 theta, so that's going to give me 7 pi over 4. And then I have minus 2 cosine, and it's 7 pi over 12 into 2 theta, so it's 7 pi over 6. Minus 1/2, and then I'm putting 7 pi over 12 into the 4 theta, so it's sine of 7 pi over 3. So I'm reducing as I go. Feel free to take more steps if you need to be careful. And then I'm putting in the negative pi over 12. And we're going to do the same thing. We're going to get negative pi over 4 minus 2 cosine of negative pi sixth minus 1/2 sine of negative pi thirds. All right, this is all unit circle values, so that's very friendly, and we can get them out of there very, very nicely. So I have a 1/2 here. I have 2 pi plus, this one's the square root of 3. So I'm consolidating. Let me clarify that. This is actually adding to this to give me the 2 pi. I have a square root of 3. I have minus the square root of 3 over 4 and minus the square root of 3 over 4. All the pieces are combining and reducing and so forth to give me these values, okay? And then I have 1/2, combine those one more time, of 2 pi, and then it's plus square root of 3. Well, actually, I'm going to consolidate them all. The square root of 3, the negative square root of 3 over 4, and the negative square root of 3 over 4. I'm going to get 3 square roots of 3 over 2. That's what it works out to being. Distributing 3 by my 1/2 gives me pi plus 3 square root 3 over 4. So super messy because we're working with so many different angle measures, and the angle measures are not super friendly. But the process is something you've seen before, just not quite so messy of components. All right, there's one other thing in this section besides looking at the area, which we were just doing, the area in polar coordinates, and that is the arc length in polar coordinates. All right, so we're going to find the arc length of a given curve. Let me go back one more, sorry, we're talking about it. And our function f is a continuous on the interval from alpha to beta. Same conditions that we had before, the length of the graph and so forth, all that's the same. What you'll notice now is that we have a square root, and it looks a lot like the ones that we were doing back in parametric. I've got a radical, and I've got a couple of things squared. But what I have squared is the original function, and I have the derivative of that function. Okay, so in another form, I have the integral from alpha to beta of r squared plus dr d theta squared, and then I have it square rooted. So one thing I want you to notice is that this means you have to find a derivative to get started. So as we look at this one, the first thing we'll do is find our derivative. So the derivative of 2, of course, is 0. And then the derivative of 3 sine of 3 theta would be 9 cosine of 3 theta. Okay, so we're going to find the arc length as requested. This is the integral. And we need to find the angle on the graph. So we probably should graph this one as well. I don't know that we've graphed, I don't think so. We haven't graphed this one yet. So grab your calculator and take a look. Okay, so again, the default would be that you're going to go from 0 to 2 pi and see what you see. If it looks like it's fairly complete, you're welcome to make it go bigger and see if you're actually getting anything more, right? Like make it go from 0 to 2 pi. 0 to 4 pi. 0 to 2 pi actually works just fine on this one. If you've taken a look at the graph, you've seen that. We have kind of a flower with some embedded flowers. So I won't draw a whole bunch of this out, but it looks like these 3 big loops, right? They're more symmetric than that. And they've each got these little loops inside of them. Looks kind of like a prettier flower, something that we had before, more detailed. So I want the square root. I want the original function, which is 2 plus 3 sine of 3 theta, and that will be squared. And to this, I will add the derivative that I just found, 9 cosine of 3 theta, and I will square it and do d theta. Okay, so you're going to like what happens eventually, but we're not going to like what happens at the beginning. It's kind of messy. So this is 0 to 2 pi. We're going to square this out, so we're going to get 4 plus 12 sine of 3 theta. And then we're going to have 9 sine squared of 3 theta. On the other piece, we're going to have 81 cosine squared of 3 theta. And then I have d theta out here. Now we are going to clean up what we can, always. Okay, so if you stop right here and then go do something else with a calculator, basically, you're going to lose some points for not simplifying what you can. Because I do have a sine squared and a cosine squared of the same angle, I do need to do a little bit of consolidation. So that's what I'll do first. This is 0 to 2 pi. And I'm going to rewrite, and I'm going to choose to rewrite the cosine in terms of sine. You could do it the other way, and that would be fine as well. So this is 4 plus 12 sine 3 theta. None of that changed, nor does the sine squared part change. But we're going to replace our cosine squared with 1 minus sine squared. Same angle, 3 theta. There we go. Move that over there. So this allows me to have 4 plus 12 sine of 3 theta. And then I have 9 sine squared 3 theta. And I'm going to have plus an 81, right? And then minus the 81 sine squared of 3 theta. So I can combine a couple things here. I can combine the 81 with the 4, right? So that gives me 85. I cannot combine the 12 sine 3 theta, so that just gets rewritten. But I can combine the 9 and the negative 81, which gives me a negative 72 sine squared of 3 theta. So here's the problem at this point. This is as simple as we can get it. Let me put that part at the beginning there, so 0 to 2 pi. This is as simple as we can get it. There isn't anything else that we can do algebraically, calculus related, or so forth, to simplify this and make it any better. So what do? Well, we actually allow our calculator to do this for us at this point. So what you're going to do is you're going to go into your calculator and you're going to hit the button that says Math 9, 8 actually, I think it is, yeah, Math 8. So you're going to be in your regular screen, you're going to hit Math 8. You're going to hit the VARS button. You're going to go over to YVARS. You're going to choose polar, that's number 3. Your polar equation is R1. Okay, so right now, like on the device I have, my calculator literally says in deriv, and I've got R1 here. There's another calculator version I'll write down in just a second. If this is your calculator, you're going to put comma. You're going to put theta. Okay. You're going to use the lower limit of integration, which is ours is 0. So a comma between all of them, comma 0. And then the upper limit of integration, which was 2 pi. And you're going to press enter. All right, scrap that. That was derivative. I definitely was meaning 9, not antiderivative, or not derivative, antiderivative. Math 9 is the one that I want. Oh my goodness. Get the right one. It says F and INT. I was like, something about this isn't working. F and INT. Okay, try again. We go through the same steps. It's VARS, YVARS, function, VARS, YVARS, polar, R1. You put the lower, or you put the theta in here. This part's all the same. This is what I was talking about. And then the 0 and the 2 pi. Okay? So comma theta, comma 0, comma 2 pi. And when we do this, we get a certain angle measure.